So I'm going to start out with a review of the quiz from last time. I took a look at the scores. Looks like everyone did well on it. The first question was, what's the size of a peripheral's I/O space whose address begins at 1100 in hex and ends at 2 CEF in hex? So you just subtract, and so I have to subtract these in hex. So you just do base 16 subtraction. So F minus 0 is F, E minus 0 is E, C minus 1 is B, and 2 minus 1 is 1. So the difference is 1 BEF, and if you convert that to decimal, which I usually just use a calculator to do that, it's 7,151 in base 10, and then you want to add 1 to that because these addresses are inclusive. Make sense? Okay. Question 2 is, suppose variable B contains the value 1, 2, 3, 4 in hex. To what value will it change after executing the code B equals B, or bitwise or 1 shifted by 5 bits to the left? So in this case, if you do an OR, remember if you OR, that gives you the ability to set bits to 1 if you do a bitwise OR. So in this case, you're taking a value of 1 and shifting it 5 bits to the left. So that's just creating this temporary value where bit 5 is set to 1, and then if you OR that with B, it just turns on bit 1 in B if it's not already on. If it's already on, then it has no effect at all. So yeah, that's it. The code turns on bit 5 if it's currently off and has no effect otherwise. Does it make sense? You guys follow that? Okay. Okay. Bit 5 is in the second least significant hex digit 3 and is in position 1. Well, that's confusing. Right. So what that means is that we're starting out with a hex value here. And so you're saying I'm going to set bit 5, but where does bit 5 land in the hex digits? Well, remember there's 4 bits in each hex digit. So if you're setting bit 5, you have to figure out where does it fall in the hex world. So the rightmost hex digit is bits 3 down to 0, right? 3, 2, 1, and 0. And so bit 5 would be 2 bits into the second hex digit from the right, the second least significant digit. Make sense? So what that's doing is putting a bit in this digit, right? Because if I subtract 4 out of this 5, because there's 4 bits associated with this first hex digit, the difference here is bit 1. So I'm setting bit 1 into the second hex digit, and bit 1 carries a significance of 2 to the first power, which is 2, right? But in that case, that bit's already set, because in order to get 3 in that hex digit, you would have to add 2 and 1, right? So the hex digit 3 is binary value 0011. And since that 5 is going to contribute a 1 bit into the bit position 1 in that hex digit, it's not going to have any effect because it's already set. Right on here? Yeah. So 0011, that's 3. And then 4 is 0100, that's 4, right? So I've taken a 1 bit, starts out here, always starts out on the right if you have 1. And I'm going to shift it 5 bit positions over, which is going to put it's already in bit position 0. So if I shift it 5 bits to the left, it's going to go 1, 2, 3, 4, 5. So it's going to align that bit with this digit, right? 0, 0, 0, 0. So what I'm going to end up doing is doing an OR, a bitwise OR between these 2 values, which is actually not going to have any effect with regard to changing the original value, right? Because you're basically just ORing 2 1s together, right? And that's not going to actually change anything from the original one. Okay, yeah, that was my explanation on the slide was kind of confusing. Suppose variable b contains the value 1, 2, 3, 4 in hex. To what value will it change after executing the code? B equals b and 1 shifted 5 by 5 bits to the left, minus 1, then shifted to the left again by 1. Okay, so we start out with the same value, except this time let's put the whole thing on there. So it's we have, so that's 1, 2, 3, 4 in hex, and so you've got the corresponding binary value for that. And so I'm going to take a 1 and shift it by 5 bits to the left. So I'm going to start out with a 1 here. Then I'm going to shift it 5 positions to the left. So that's going to give me 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So after doing that, the hex value there is 1, I'm sorry, not 1, 0. Is 0, 0, 2, 0, right? So having a 1-bit shifting at 5 bits to the left gives me hex value 0, 0, 2, 0. But then I'm going to subtract 1 from that. Okay, so what happens if I take this expression and subtract 1, it's going to end up, upper bits won't change. Okay, unless I subtract 1 from, unless it rolls the odometer over backwards. But in this case, it's not going to happen. I'm just going to decrement. I'm going to end up with, I'll go from 2, 0 to 1F. Right, so if you have 2, 0 in hex and you roll it back by 1, you decrement it by 1, you get 1F. Okay, but then I'm going to take that 1F and shift it to the left by 1 bit. So what I have here is 1, 2, 3, 4, 5 bits that are turned on. All 5 of those bits are right aligned, but I'm going to shift all of those bits over to the left by 1. So I'm going to get 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0. So basically when I shift to the left by 1 bit, I insert a 1 in the rightmost position, and the other bits move over by 1 position. Okay, so the hex value there, which is probably not relevant here, but I'll just put the hex value here, 0, 0, 3E, right? But that doesn't really help me because I'm going to do a bitwise operation here, which is to do an AND. Okay, so if I take the original value and I do a bitwise AND with the final value here, the final temporary value, that's going to mask off bits, what is this, bits 5 down to 1. It's going to mask off, meaning that when I apply this mask by ANDing it with the original value, it's going to zero out all the bits in the original value except for bits that are in the positions 5 down to 1, these guys. So what is that going to give me? It's going to give me all zeros up here, all zeros in the next digit to the right. Okay, now that's still going to be 3, right? Yeah, 0, 0, 1, 1. So when I take this digit 3 and I AND it with 3, right, it's just going to be 3. And then this guy is going to still remain 4 because the single 1 bit that's set in there is aligned with one of the 1 bits in the mask. So that's still going to be a 4. Okay, you guys can see that over there. Sorry. Okay, so that gives me a hex value of 0, 0, 3, 4. That's the final value. See that? Does that make sense? I know you probably couldn't see all that. Okay, so, all right, so 1 shifted by 5 minus 1 gives the binary value 1, 1, 1, 1. So if I shift a value, if I shift a single bit by n bits to the left and then subtract 1, I just get a sequence of n 1 bits, right? So if I want 5 1s, I take 1 shift by 5 and subtract 1, and that gives me just 5 1 bits. And then when I shift that value to the left by 1, it basically just inserts a 0 on the right-hand side and moves the other 5 bits up. So instead of, originally this mask was set up to mask off bits, what would this be? 4 down to 0, right? If I count from the right, starting at 0. So 0, 1, 2, 3, 4. So bits 4 down to 0 are going to be masked off, except I shifted it. So now instead of 4 down to 0, it's going to be 5 down to 1, right, as the range of bits I'm masking off. And so all of the bits in the original value that are in the positions 5 down to 1 are going to be retained. The other ones are going to be zeroed out. And so in the case of this value, that's going to zero out the 1 and 2 because those are in bits 15 down to 8. 1 and 2 are bits 15 down to 8. And then 3 and 4 are bits 7 down to 0. And I'm masking off bits 5 down to 1, except all of the 1 bits in 2 to 3 just happen to fall within the range of 5 down to 1. So basically you end up with just 0, 0, 3, 4. Okay? If you have any questions, let me know. Feel free to stop me. I'm going through this kind of fast. Okay, suppose you want to set bit 3. I guess I had a typo there. You want to set bit 3 in the variable b to 0. Which line of code will accomplish this? And there were some options there. So if you want to set bit 3, you're going to take a 1 bit and shift it by 3 bits, and then do a bitwise complement, and then do an AND, which would be this one, right? 1 shifted by 3 bits to the left, that just sets a bit 3. But then you have to do the complement because you want to have everything 1 except for bit 3, because I want to 0 bit 3 out. And so that's what this little tilde does. And then, oh, sorry, then you don't OR it, you would do an AND. So actually the correct answer is D. So D, it says B equals B and the complement of 1 shifted to the left by 3 bits. So this will turn off bit 3. Okay? Okay, suppose there's a 32-bit variable named IOStat containing a bit field 4 down to 2 that you need to read. What expression will accomplish this? Okay, so this one, I have different, I try to graphically illustrate this. So in this case, you say IOStat and with 1 shifted by 5 bits to the left minus 1. So this will give me a chunk of 5 1 bits. And then I'm going to do what? Shift it and then complement it? Or I'm going to complement it and then shift it? I believe the order of operations here is the complement would happen first, right? Obviously, this sub-expression would be evaluated because it's in parentheses. But then you have to figure out whether you're going to be doing you're competing between doing the complement or the shift, depending on the operator precedence. So I usually have to look this up. I just Google C operator precedence because for some reason I can never remember this. But the complement, complement I believe is first. So that's going to complement, it's going to give me all 1s except for the rightmost 5 bits, which will be zeroed, right? That's what this does. And then I shift it 2 bits to the right, which is, I don't know why I would do that, but that would end up giving me all 1s. Oh, actually, it'll give me some, actually, I'm not sure if I would shift in 0s or 1s here. So this right shift, the question is that an arithmetic or a logical right shift, right? What would be shifted in, zeros or the sign bit? Obviously, the sign bit would actually be 1 here, right? Because this is basically all 1s except for the low order bits, which I turned off. So I think the question is what type C, if we're writing this in C, what type the C compiler would associate with this sub-expression, which is difficult to tell because they're all constants in there, right? There's no variables. So if it was a variable in there, then you can assume that it would use the type of the variable, but I don't know there's no variable. So I'm not sure. I'm assuming it would, I'm guessing it would assume these are signed constants by default, and so it would end up doing an arithmetic shift. So what you'd end up here is all 1s except for some 0s on the right-hand side, and you'd get, instead of 5 0s, you'd get 3 0s because you'd shift 2 of those out. Anyway, so the explanation I have here is turns off all except bits 4 down to 0, and then shifts the result to the right by 2 bits, leaves the original bits 31 down to 5, and positions 29 down to 3. I'm sorry. I had that wrong. Back up. Let me correct myself. So it turns out that after the complement gets done, the ampersand is actually going to happen and then the shift. Sorry, I had that wrong, right? And actually that makes sense because there are parentheses here around this sub-expression, right? So I do the mask and then I shift 2 bits to the left. Yeah, sorry about that. So basically this turns off all bits except for 4 down to 0, and then it shifts the remaining value, or whatever's the result of that, to the right by 2 bits. Yeah, sorry about that. Make sense? Yeah, I'm sorry, I missed these parentheses here. The point is you have to be careful about, the operator precedence. In any case, I don't think that's what I want to do anyway, though, right? No. That wasn't my objective, so that's not the right answer. Okay, so this one, option B is to take IOStat, shift it to the left by 27 bits, and then shift the result of that to the right by 29 bits. Now you might think, well, why would you do that? That seems kind of silly. The purpose of that is by shifting it to the left, you're going to shift off all the bits to the left of the field that you're interested in. And then when you shift it back to the right, you not only eliminate all the bits to the right of the field you're interested in, but you also right align the field that you're interested in. You push it to the right-hand side of the variable. So I tried to show that here. So if I shift to left by 27 bits, I'm going to take 4 down to 3 and move it all the way over to the left-hand side, where it will now be in bits 31 down to 29. Okay? You might say, well, wait, how'd you know it was 31 down to 29? Because, how did I know that? Well, it was because I'm going to get rid of 27 bits, right? So if I have if my highest bit value is 31 and I subtract 27, I end up with 4, right? So if I shift to the left by 27 bits, my new most significant bit will be bit 4 from the original value, right? Because of, again, 31 is the most significant bit. It's 31 down to 0, right? But the problem with doing that is that even though I eliminated all the garbage bits to the left of that field I was interested in, 4 down to 3, I still have bits 1 down to 0 would have been tagging along. So the 2 bits I don't care about are, bits 1 down to 0 are hanging out here in bits 28 down to 27. So I can shift to the right by 29 bits, which will move it all the way back to the right, and it will delete the original bits 1 down to 0. Make sense? Now the problem with that is, notice I say all zeros here. So the final value, you would expect to have all zeros in bits 31 down to 3, right? But actually, that's going to depend on which shift instruction was used. If it was, did you guys cover arithmetic versus logical shifts when you took 212? Or 212? In arithmetic, so when you shift to the right, the question is, what are we filling in here? What are these bits going to be on the left when you shift back to the right? It would be zeros if you do a logical right shift. But it would be the sign bit, which would be whatever bit 31 was here. If you do it would get dragged across if you do an arithmetic shift. Now you might say, well, how do I know which one I'm doing if I'm not writing in normally the way you'd know is you look at the instructions, right? The assembly code instructions, right? Because there's 2 different instructions. But if you're writing this in C, how would you know? How would you know how the C compiler did it? Which instructions the C compiler generated? Well, that would actually depend on IOStat. If IOStat is an unsigned variable, if it was declared unsigned, or if the C compiler thinks it's unsigned, views it as unsigned, then it would do a logical right shift, in which case you're guaranteed to have all zeros here on the left side. If it thinks that that's a signed value, then it's going to apply a shift right arithmetic, in which case you may end up with all ones here, right? So that's something that you can define in your code. You can, it's not shown here because it doesn't show where the declaration of IOStat is. You guys with me? So this question's a little bit, probably could have been written a little better here because it's not, of course I might have a better answer. Actually, hold on before option C is all of these. And then option D says IOStat shifted by 2 bits to the right, which will basically just eliminate bits 1 down to 0. and push the original bits 4 down to 2 down into the rightmost 3 positions. And then I'm going to do a bit mask with 7, 1, 1, 1, and just bit mask out those 3 bits. So this is actually a better one because this one doesn't rely on whether it does a arithmetic or logical shift. So this is the correct answer, right? The other answer I had on there, the shifting one, was good, except it had that potential issue of, dragging the sign bits in, when you do the shift back to the right. Oh, and there was another one here. Shift 2 bits to the right and then do a cast 1 shifted to the left by 3, which is 8, numerically is an 8. Subtract 1, you get 7, and that ends up doing the same thing. So actually, I guess the right answer was all of these, right? So I guess I was wrong about this one. So let's revisit number A here. So IO-stat, so I took 1 shifted by 5 bits to the left, that's going to give me 32, right? The numeric value 32, 2 to the 5th power. Minus 1 is 31. 31 in binary is just 5 1 bits. Then I shift that 2 bits to the right, and I'm just going to get 3 1 bits, right? But I'm wrong because I don't do that. First I take IO-stat and I mask it. So I mask off the low order 5 bits, which is this sub-expression, and then I shift it 2 bits to the right, which then will give me the bit field that I'm interested in, right? So yeah, I didn't give this option enough of a chance. Does that make sense? You guys follow that? So the point is that they all do the same thing, except for the possible exception of this one. This is not as good of an answer, I don't think. But that one works, and that one works. So yeah, technically they all work to give you that field. So the point is that there's multiple ways to extract bit fields. Okay, which of the following bit sequences show, okay, so this one talks about pulse width modulation, and I realized today that I hadn't covered that last class, so I just gave everyone credit for that question, regardless of how you answered it, because I didn't get far enough in the lecture. So I will cover that today, though. So let's go ahead and go and do that. Okay, so last time we talked about programmed I/O. Now this can get a little confusing. So with programmed I/O, the point of that is that is the way that the software talks to the hardware, right? It's the way that the software exchanges values with hardware peripherals. From the software perspective, right? That's what your code is going to be doing. Today, we're going to be talking about how the peripherals can talk to other peripherals. We're going to start talking about I/O protocols for doing off-chip communication from the hardware perspective. So this class mixes together hardware and software, right? Programmed I/O is a software concept. You read or write to certain addresses, and that exchanges data with hardware, right? But there's also this notion of I/O pins and signaling between I/O pins. That's kind of those are typically implemented in hardware. The protocol, unless you do bit banging, if you've ever heard that expression. Bit banging is when you write software to actually implement low-level protocols, which is also possible. But fundamentally, the way you do that is you're still doing programmed I/O. You're just doing programmed I/O to set a pin to 1 or 0, and then going through a sequence doing that. It's called bit banging. But anyway, so programmed I/O is loads and stores to special baked-in address ranges, which are I/O ranges, to talk to peripherals. And we mentioned that, and then we also talked about when you're doing that, you have to typically do bit manipulation as part of that in the software. So we talked about how to do that. We talked about a few ways of doing that. There's multiple ways of doing that. Okay, so then today we're going to dive into the hardware a little bit. So yeah, programmed I/O and bit twiddling was last time. Bit twiddling, bit manipulation, same thing. Today we're going to talk about 4 topics. Pulse width modulation, which is a way that you can create an analog signal with a digital pin. It's very common in cyber-physical systems. Interrupts is a way that it's a feedback signal. It's a way for the hardware to get the attention of the software, basically. An interrupt is a wire that allows a hardware device to say, hey, I need service. So normally with programmed I/O, that's all driven by the software, right? Software does reads or write to hardware, but the hardware just responds to it, right? It just responds to programmed I/O. The problem is that if you do that, if that's your only mechanism, there's no way for the hardware to initiate communication with the CPU, and that's what interrupts do. And then we'll talk about interface protocols, which I just talked about. And then I'm going to try to get far enough here to get you ready for lab 1, which will start in the lab this week, the first project, coding project. Okay, so pulse width modulation is actually, you guys might already be familiar with this. It's a pretty simple concept. It's a way, if you have a digital pin, which is 1 or 0, high or low, right? If you have a digital pin, which can only have 2 different levels, right? How do you make that dim an LED? Or how do you make it talk to a voltage regulator, power converter, like AC-DC converter, or a voltage regulator, or a buck converter, that sort of thing. Power electronics, any kind of like amplifier, that sort of thing. Or how do you make it play audio? Like if you go to the grocery store and you get one of those cards that you open up and it plays a song, how does that work? Because the little controller in there is just digital, right? How do you do analog? Audio rather, with digital pins. And then motors and servos very often will have a PWM signal. So if you want to, like robotics, if you have a robot, you know, the degree to which the robot moves is dictated by this, is driven by this thing, pulse width modulation. So it's basically, to summarize what it is, it's a way that you can have a digital pin drive an analog device without having to have a complex digital to analog converter, which is, you know, expensive, right? So the way PWM works is it's basically a clock signal. It's a periodic signal, rather. It looks like a clock signal, if you remember that from 212. In that, it basically just switches between high and low logic level. And it does it according to a period. The period is measured, is the repetition interval, right? And it's measured, you can measure the period from like the rising edge to the next rising edge, or from the falling edge to the next falling edge. That's the period, right? So the period is measured in time, and if you take the reciprocal of the period, that's the frequency, switching frequency, right? So a PWM signal can have whatever switching frequency you want. Usually they're like tens of kilohertz, right? Which is like tens of kilohertz, hundreds of microseconds or something like that, right? It's the inverse, right? But with PWM, unlike a clock signal, that usually has a 50% duty cycle, meaning that half the time the clock is high and half the time the clock is low. With PWM, the duty cycle actually represents the analog value that you're putting out. So for example, if I have a 10% duty cycle, it means that the signal is high for 10% of each period, right? So each period it's high for 10% and it's low for 90%. And so if the switching frequency is high enough, then basically you end up with an analog signal which is 10% of whatever your high voltage level is. Make sense? And of course you can go all the way from 0 duty cycle, which is just, you know, you never go high, to 100% duty cycle where it's always high, or anywhere in between. Now the PWM signal, some of you guys I'm sure have seen like LEDs that dim, like that pulse, that get brighter and dimmer, like those ones you hang up on your wall, right? Those ones use PWM. So what that implies is that the PWM duty cycle is dynamic. It can change. Like if you have a pulsing light, you know, it gets brighter and then dimmer, brighter and then dimmer. So that duty cycle is changing over time. But if you looked at the individual periods, it would take it a long time to change. In other words, so the point is that what I'm trying to say is that the frequency of the PWM signal is much, much higher than the dynamics of the changing of the PWM. So if you look at your LEDs that are getting brighter and dimmer, that's much slower than the switching frequency of the PWM signal. Make sense? Okay. So in other words, what I'm saying is that like if you have a 25% duty cycle now, but you want to brighten your lights, you'll have a 25% in this period. When you go to the next period, you'll have slightly more than 25%, right? So this period, rising edge to rising edge, you'll have 25.0001%, right? And then you get to this one and you'll have 25.0002%, right? So the duty cycle can change over time, right? But it's measured over a over what the percentage is over the period of the signal. Now the period is kind of arbitrary usually. Usually you want it high, but there's a point of diminishing return. You know, you don't get any benefit from it being super high, right? Now with regard to audio, if you try to do audio over a PWM signal, which is how Class D amplifiers, I don't know if any of you guys are into like, you know, stereo equipment, but you know, they have Class AB amplifiers for like cars and home audio, and then there's the Class D amplifier. Class AB is more of a rectifier, but Class D is actually using a PWM signal. But you can't just run this straight to a speaker, because the problem is the speaker will pick up the frequencies from these steep switching, right? So if you use a PWM signal to drive a speaker to actually play music, you have to put a low-pass filter on there too to filter out any kind of artifacts you get from the switching, right? But the speaker will still play, you know, the frequencies that are being modulated into this duty cycle over time, right? And that's why if you go to the grocery store and you open up one of those greeting cards, it sounds a little weird, a little tinny. The sound quality isn't great, because usually I don't think those have the filter at the other side. I think they drive PWM directly into a speaker. But if you have a high-end stereo system at home that has a Class D amplifier, which are really nice because they're efficient, but they're not quite as, you lose some of the audio quality, but they're very power efficient. But anyway, Class D amplifier for audio will have that low-pass filter that'll take away the artifacts from the switching. But the point is, this is basically what you end up as an analog signal. Okay, so anyway, question. What analog voltage is generated from a 3.3 volt PWM signal? 3.3 volts referring to the high voltage level, right? If the high voltage is 3.3 and the low voltage is 0, and you have a 30% duty cycle, then the answer is 3.3 times 0.3. It's 30% of your high voltage, right? So you end up with 0.99 volts effective, right? Okay, so that's it. That's all there is to PWMs. Next topic is interrupts. So an interrupt is a way for a peripheral to get the CPU to do something. They're needed like if a network, things that the CPU can't predict, right? Like if a network packet is received from the network, or a user hits a button on the keyboard, or some kind of, or a timer goes off, or some other peripheral wants to talk. These are interrupts are used for that. So an interrupt is basically a signal that goes from peripheral to CPU, and it tells the CPU to, when the interrupt activates, the CPU should go into its interrupt handler, right? Which is usually in the operating system. If you don't have an operating system, then you just have an interrupt handler that you've written inside the code, okay? So keystroke, network packet, yeah, I think I said that. Disk transfer is completed. Yeah, so you got this basically a wire, okay? So what happens is that if I have an interrupt wire, you know, let's say that normally it's logic 0, logic low, right? And the CPU is just running, it's doing its thing, right? Running whatever code it wants to run. And then you can have, for instance, what's called a level triggered interrupt, which is when the CPU is expected to go into the interrupt service routine, the ISR, relatively soon after the interrupt goes high, right? And then it finishes the ISR and goes back to whatever it was doing. That's pretty straightforward, right? Now there is a problem with this though, because this is only, there's no coordination, there's coordination between the interrupt pin and the CPU, but not the other way around. So the problem here is that the peripheral does not necessarily know when to drop this. It has to keep this interrupt pin high enough to get the CPU's attention and guarantee the CPU services that interrupt. But if you leave it high too long and the CPU gets done servicing the interrupt and it's still high, then what happens? Then it might think, oh, there's another interrupt when there actually isn't. So this is a little dicey. Like how long do you leave this thing high from the peripheral point of view, right? That's a little that can be a problem. You can also have an edge-triggered interrupt which responds to the rising edge instead of the level, right? Which is a little bit better because then if the interrupt does finish before the peripheral drops that interrupt line, it's okay because it's not going to see another rising edge again until the next legitimate interrupt, right? So that's one way to solve that problem. Now this, by the way, these interrupts are the style that's used in the Arduino, just so you know. We got these from the Arduino, and that's exactly how it works. In fact, you can program the Arduino to be level sensitive or edge sensitive, depending on what you want. Okay, so here's a question. Suppose a peripheral is connected to the CPU's external interrupt input. Assume the peripheral can change the value of the external interrupt no more frequently than once every 50 microseconds. Meaning, when I say change, I mean change it from low to high or high to low. Assume the CPU can execute its interrupt service routine in 75 microseconds. What's the maximum number of interrupts per second possible when using rising edge triggered interrupts or level sensitive interrupts? Okay, so for rising edge triggered interrupts, the problem here is that you can only change the interrupt every 50 microseconds. So that means that in order to get a rising edge, you have to be, if you're already high, you have to go low and then high again, right? So you got to go from high, you go high, 50 microseconds, low, 50 microseconds, high, 50 microseconds, right? So the problem is if you've got edge triggered, let's see here, 50, 50, 50, low, high. So I've got the minimum is 1 over 75 or 1 over 50, and this is looking for the minimum in terms of frequency. So the 75 obviously refers to the service time. So I can only service it in 75 microseconds. So 1 over 75 microseconds is 13 kilohertz, right? So I'm limited to 13 kilohertz based on how fast I can actually run the interrupt service routine. And then this is meant to represent how fast I can actually trigger the interrupt, right? And so that's, I've got 1 over 50. Now I would have assumed that'd be 1 over 100 there. Because this is edge triggered, so you got to go, if you're edge triggered, you have to, if you're changing it every 50, I think that might be, I think I might have these, yeah, I think I have these swapped, sorry. Let's double check that. So for level sensitive, I had 100 there for the, you know, how fast you can actually change the line is 100. So with level sensitive, you know, with level sensitive, you can just leave it high, right? Like if it's level sensitive and you want to execute interrupts as fast as possible, you just set it high and you leave it there, right? Whereas with edge triggered, you need an edge. So you can't just leave it high. You have to be high, low, and then high again, right? So I think these are actually swapped. And not only are they swapped, but the I think I would argue that the level sensitive should be, you know, you could execute that, you know, infinitely fast if the limitation was just how, you know, the actual wire. Make sense? You guys with me? Okay. Okay, and then another thing is that even if you have edge triggered, so this is an edge triggered interrupt where I have an edge which causes the CPU to go in the ISR. Let's say that I did want to go crazy and I wanted to try to get the CPU to respond to very rapid interrupts, right? Very frequent interrupts. So I could have an edge here and then I can go down and I can have another edge. So this is the peripheral trying to tell the CPU to interrupt twice, right? There's 2 rising edges, right? The problem is that the CPU, it's slow. It takes a long time to execute the interrupt service routine. So by the time the interrupt service routine is finished, it's actually missed the second interrupt, right? Because it was too slow. So a way to deal with that is to use, and of course the same issue happens, I kind of alluded to this earlier, whereas if you have a level sensitive interrupt, you can put the interrupt high and leave it high for too long and accidentally trigger 2 interrupts when you don't, you know, trigger 2 interrupts on the CPU when you only meant to trigger 1. So in this case, you're triggering too many. In this case, you're only triggering one when you meant to trigger two, right? That's because there's no coordination between the CPU and the peripheral aside from just the one interrupt line. So more sophisticated CPUs, I mentioned this is how Arduino works, but more sophisticated CPUs like the ARM processor in your phones have an acknowledgement line. So for every interrupt, there's an acknowledgement. So that way, the acknowledgement is a way for the CPU to acknowledge the interrupt and to tell whoever's sending the interrupt that I got it. You can drop your interrupt line now, right? You can drop it. So in this case, the interrupt would have a rising edge. The CPU might take a little while before it actually, there might be a latency there before it actually processes the interrupt. But once it does, it'll give the peripheral a rising edge of the acknowledgement. So this is a feedback, right? So, okay, I see your interrupt, right? And so the CPU, the peripheral will then respond to that acknowledgement by dropping his interrupt request, right? And then, yeah, so that's a way to prevent, that issue of the peripheral triggering too many or not enough interrupts. Okay. Oh, and by the way, the CPU also will drop its acknowledgement after it sees confirmation that the peripheral dropped its interrupt. Yes. It adds wires is the problem. It adds wires. So these are wires. Now, it's not necessarily, it could just be on-chip wires or it could be off-chip wires, but yeah, that's the main cost there is wires. It adds another wire for every peripheral. Yeah. Okay, so now we're switch topics again. So last thing I want to talk about, I want to introduce this idea of interface protocols. So in this, there's a lot of interface protocols. That's basically how chips communicate or digital devices communicate through these protocols. In this class, we're focusing on ones that are for embedded systems. So they're relatively low speed and usually serial protocols, right? So these are the kind of protocols you might have in your car. The car, devices in your car communicate that uses controller area network CAN, or relatively low speed. We're not going to look at things like PCI Express. I'm sure you guys are familiar with PCI. That's how your video card connects to your computer. Or QPI, Rapid I/O. We're going to focus on the sort of the embedded systems versions of these. And so there is a trade-off here. I mentioned at the beginning of the course there's a trade-off between, with these interface protocols, the longer distance you go, the slower it's going to be, generally speaking. So if you have components on a chip, they talk through something called AXI. That's the ARM protocol for on-chip networking communication. That's very fast, very high throughput, low latency, but it's on a chip. Then you've got chip-to-chip protocols, which are the ones like PCI and QPI that are communicating between different things on your motherboard, right, on your circuit board, chip-to-chip. And then local area network, this is where you're going from computer to computer, and that's longer distance, and you're generally going to be you're going to give up some performance with that just because of the distances involved. With these we're going to focus on chip-to-chip channels or bus protocol. I might say channels or protocol is the same thing. It's basically a communication technology, right? And so there's two types of these that we're going to be talking about. There's asynchronous and synchronous. Asynchronous protocols have no clock in the channel, right? Synchronous have a clock. There's advantages and disadvantages to having one or the other, depending on your application. PCI, which is the high-speed bus inside your computer, is actually asynchronous, believe it or not. There's no clock in there. But yet it's still very high speed, and the reason, the way they do that is they use a encoding scheme. All the data is encoded using 66, 64-bit encoding. And that encoding is designed to add some extra bits adds some redundancy, but it maximizes the number of transitions in the data. So that as the data is sent through the channel, you want to have a lot of transitions in that data, right? As opposed to saying, oh, I want to send a bunch of zeros, and then you just get 0, 0, 0, 0, 0, 0, 0, there's no transitions. In the encoding format, if you do send zeros, you don't get zeros, you get a code word that has transitions in it, right? And so in those cases, PCI actually extracts the clock signal from the data using a circuit called a phase lock loop. So that's an example of an asynchronous. Asynchronous is that when you actually have the clock embedded in the actual channel. And so the first protocol we're going to look at is called SPI, and it is a serial protocol. It has the clock, synchronous protocol. It has the clock. SPI stands for Serial Peripheral Interface. It's a very common interface for chip-to-chip communication. And it is a, SPI is similar to program I/O, where you have two sides of the channel. You have an initiator, which is called the master, and then there's like a peripheral or something on the other side that's a slave. And the slave just responds to the master. The master drives everything. So the model that's being used here is that the master is the CPU and the slave is the peripheral. There's no way for the peripheral to initiate a communication with the other side. It only responds unless it has an interrupt, right? So you can have an interrupt coming back. But SPI is meant to implement like this programmed I/O style communication. Okay, so a channel then consists of 4 wires. There's a clock because it's synchronous, and then there's MOSI, master out, slave in, and MISO, master in, slave out, and then slave select. So this is a bidirectional, this MOSI and MISO are data that go in both directions. So there's a bidirectional data. So both sides of the channel communicate, send data simultaneously. But the reason why only the master can initiate is because the slave select is what actually initiates communication. And that only goes from the master to the slave. So that's the reason for that. And then the clock is just the clock. So there's 4 wires here. And so in order to understand how this works, you have to be comfortable with reading timing diagrams. The timing diagram, and you might have seen some of these already in 212 or 211. A timing diagram is a plot where the horizontal axis represents time, the flow of time. So from left to right, you've got time advancing. And then you have the signals are plotted. And if you have parallel signals, in this case we have 4 parallel signals, they're just shown on top of one another because they're all operating in parallel, right? And then you have each signal can be high or low. Now in this case they're all binary. So if you had a multi-bit signal, there would actually, you can have multi-bits and have more than one, just 2 levels there, 2 values. But these are all binary signals. So they're all just high or low. And so what's happening here is you can see that this SS, this slave select is high at the beginning. It's high by default. So when the channel is idle, when there's no communication, it's logic 1. It's high, right? And whenever you want to initiate a communication, the master drives it low, right? So it's very easy to tell when there's communication. You just look for this thing being low for a period, right? And when it's low, the clock runs. When the slave select is not asserted, the clock is idle. It just flatline, right? So this is a way to make the technology a little bit more efficient, is that you don't have to alternate the clock. You don't have to keep toggling the clock when the channel is not being used, right? And then the MOSI and MISO are just going to be sending data, right? Now they're only 1 bit because this is a serial protocol. So even though I want to send 8 bits, for example, I can only send 1 bit at a time. And so the problem here is that in order to understand what's being sent through the channel, you have to read each bit in order for each clock cycle. So what you have to look at this from left to right, because time is flowing from left to right. So MOSI is 1 0 1 0 0 0 1 1, and then this is a don't care here, this gray area, right? So you have to read each bit from left to right because each of the bits in the word, in this case I'm sending an 8-bit word, and I'm sending it in 8 cycles, but it's serial, so you send 1 bit at a time. So you have to read each bit and then assemble them all together into a final, value you send, right? And so the idea is that every time you initiate communication, you send data both directions. The MOSI sends it that direction, and MISO sends it back. So what you have is an exchange. So this is called an SPI exchange. Every time you do communication on SPI, for every bit I send, I get a bit back, right? So there's an exchange. It's like I send you 8 bits and I get 8 bits back, right? So this whole thing is called an exchange. I want to emphasize that, okay? Now, one of the confusing things here is that SPI channels can have different settings called CPOL and CFA, okay? These are called timing modes. And this is wildly confusing, and I don't know why they did this, but it's like unnecessarily complex. But basically what it means is that CPOL is called clock polarity, and it defines what the idle state of the clock is. So I mentioned the clock doesn't run if you're not doing a transaction, if you're not actively communicating. The question is, I mentioned that slave select is high by default, right? But what is clock by default when it's not being used? Well, that's what CPOL defines. If CPOL is 0, it means the clock is 0 when there's nothing going on, when the channel is idle. And if CPOL is 1, it means the clock is high when there's nothing going on in the channel. And CFA is clock phase. And now this is the one that's even weirder. CFA determines when the data changes relative to when the clock changes. Okay, so if CFA is 0, it means the data changes 1/2 clock cycle before the clock changes. And if CFA is 1, it means that the data changes, it begins changing when the clock changes. Okay, so let me show you what I mean by that. So notice that, first of all, notice CPOL is 0, so the clock is 0 before anything happens here, right? Also notice that the data goes from being gray, which is called don't care, right? I don't care what it is when it's gray, and it changes to 1. 1 is the first bit I want to send, right? But that happens 1/2 cycle before the clock goes high. So you might say, well, who cares? Why is that important? The reason that's important is because it's going to tell the receiver when to sample the data. The receiver has to know when to sample the data. So the receiving side, and by the way, both the transmitter and the receiver, the master and slave, have to agree on these settings before anything will work, right? You have to pre-establish this stuff, right? So in other words, if you buy a new peripheral and you attach it to your CPU, you got to make sure you set up your CPU to the same settings as the peripheral, right? So you got to read the documentation, essentially, and know how to set it up. Okay, so what's happening here is that if in this setup, that means that on the first rising edge of the clock, the first edge is going to be a rising edge because the CPOL is 0. On the first rising edge of the clock, I'm going to capture the data on the receiving end. Make sense? Actually, on both ends, because the receiving end is MOSI and the sending end is MISO. Does that make sense? Now, why is that important? Why is it important I know what edge of the clock? The reason it's because of something called metastability. In a digital circuit, when you read a data, when you clock data with a flip-flop, I know you guys didn't talk about this in 211, because this is more of an advanced topic we do in 611. But when you sample data, when you capture data using a flip-flop, you want to make sure that the data is stabilized before you capture it. It's got to be stable. You don't want the data changing too close to the clock edge or at the same time as the clock edge. Because if it does, you capture the data in a random state. It's called, you go into metastability. You have to make sure that the data is stabilized for a setup time before the clock edge and is stable for a hold time after the clock edge. And the setup and the hold time combined are called the aperture time, right? This is to guarantee that I get good data on the receiving end, right? So it's very important that I have the data set up and stabilized before the clock edge and after the clock edge. Make sense? It's important because otherwise you're going to get errors. If you go into metastability, it's not catastrophic, because even if you go into metastability, it just means there's a temporary confusion at the receiving end that will get resolved with time. But it will mean that you're going to get a bit error. You're going to get an error, a transmission error, right? So in order to avoid these transmission errors, it's important for the receiver to know exactly when to sample the data, okay? Now the difference, though, is that let's say that C-pool was 1. If C-pool was 1, the only thing that would change is that I would sample the data on the first falling edge of the clock instead of the first rising edge, because C-pool would start out high instead of low, right? It makes sense? So that's the only difference. But C-fa, on the other hand, let's say C-fa was 1. If C-fa was 1, then that means that the data and the clock are going to first change at the same time, which means C-fa, if that's 1, it means that I don't sample on the first clock edge, I sample on the second clock edge, whatever that is, rising or falling. Okay? So let's look at an example of that. Actually, these are all 4 configurations. Okay, so the one that we looked at was this one. Let's look at this one down here. This is when C-pole is 1. C-pole is 1. Notice the clock starts out high. Up here, it started out low. But C-fa is 0, so I'm still going to sample the data on the first clock edge. The only difference is the first clock edge is a falling edge instead of a rising edge, right? But over here, I've got C-fa 1. So notice here, the clock changes and the data changes at the same time. As opposed to over here, notice the data got a head start. The data had a half-cycle head start on the clock. But over here, the data didn't have a head start. The clock and the data both simultaneously changed. Okay? You guys with me? All right, so what does that mean? That when C-fa is 1, I sample on the second edge. Now you might say, what is that, a rising or falling? Well, it depends on the C-pole, right? So the second edge, if C-pole is 0, the second edge is falling. Because remember, it starts at 0, goes to 1, that's the first edge, goes back to 0, that's the second edge. If C-pole is 1, the second clock edge is rising, because you start out 1, you go to 0, then you go back to 1, right? So depending on those 2 settings, it's going to tell the channel when to sample the data. Because I'm assuming, the assumption here is that the sampling is activated by the clock edge, as opposed to the clock level. Everyone with me? You might say, what about clock level? We'll talk about that in I2C. I2C uses the level. That's another protocol. But in SPI, the assumption is the data is read on the edge of the clock. The clock's edge is what captures the data, is what triggers the capturing of the data. Okay? Okay. The other thing, too, is SPI does not define what order the bits come out. Remember, I mentioned you have to read each one bit at a time from the channel because it's serial. But do you go from left to right or right to left? Well, that depends. In this case, I have most significant bit first, which means that I read from left to right. So the data is going to be, for MOSI, it's going to be 0, 1, 0, 0. There's 2 cycles here, right? 1, 0, 0, 0. Right, so I read from left to right because most significant to least significant. However, I might also set it up where, oh, sorry, here it is. So this is annotated. So here's MISO. Remember, MISO is the back channel, back to the master. In order to interpret this, I have to read each one bit. Now, notice that these lines, you might say, wait a second here. If C-fa is 1, you should be reading on the second edge of the clock, right? Which is here. So why'd you draw the line here on the first edge of the clock? The reason I did that was because what I'm trying to show here is that the sampling happens between these 2 lines, these dotted lines, right? I added these dotted lines. I want to read the data between the dotted lines. So I placed the dotted line beginning on the first edge of the clock because CFO was 1, right? And now you might say, well, do you have to do that? No, I think you could probably read this without the dotted lines, right? You could probably figure it out, right? But with the dotted lines, it makes it a little easier to read. So that's clearly 1, 0, 1, 1, 0, 1, 0, 1, right? Okay, and then if I convert this to hexadecimal, it'd be B5. I just grouped the two groups of 4 bits into 2 digits, B5. So I'm getting B5 back, and then the data I'm sending is something else. The data I'm sending is 0, 1, 0, 0, 1, 0, 0, 0. So that would be what? 4, 8 in hex is what I'm sending. So I'm sending 4, 8, I'm getting back B5. That's the exchange. You guys with me? Make sense? Okay. Okay, here's another question. In the following SPI, what's the value sent from the master to the slave? 1, 0, 1, 0, 0, 0, 1, 1. So 1, 0, 1, 0, 0, 0, 1, 1, which is A3. A is, 1, 0, 1, 0 is 10 and, 10 in decimal, or A in hex, and 3 is 0, 0, 1, 1. Okay, so that's pretty easy. Now you might say, well, what does the CFA and CPOL have to do with the way that you interpreted that? Basically, it was just where I drew the lines, right? But even if I hadn't drawn those lines, you can see there's a pattern, right? There's a, because the data is always stable for 1 cycle, regardless of when it's supposed to be read, right? So the CFA and the CPA and the CPOL are important to understand about what edge the data is being sampled on. But when it comes to just reading the data, you could pretty much just read this, right? You could just see it, and it's in the waveform. You just have to identify these, these intervals of 1 cycle each. Now it gets confusing though if you have, like notice this meso has 0, 0, 0, 0. It's 4 consecutive zeros. And if you look at that without these lines on it, it's kind of hard to tell. Is there 3? Is there 4? Right? It's kind of hard to tell how many zeros there are. So you have to look up at the clock and see, oh, there's 4 clock cycles there. Okay? Okay, so now I mentioned that SPI does an exchange. Every time you initiate communication, there's an exchange. There's always an equal amount of data sent in both directions. So it's kind of a balanced transaction, right? Exchange. It's an exchange, right? The problem is I also mentioned that you're using SPI generally to do programmed I/O, right? I want to load a value from a peripheral. I want to store a value to peripheral. So the issue there is that how do I use SPI to do programmed I/O? Like when do I send the address versus the data? Like isn't there an address and there's a, programmed I/O is an address and data, right? Whether you load or store, there's got to be an address part and a data part. How do you do that when you're just pretty much exchanging 8 bits, right? That don't make any sense. So in order to make that work, you have to build another protocol on top of SPI called the transaction protocol. And so for that, you basically you do 2 exchanges, at least 2 exchanges, sometimes more. But the first exchange is when you send the address, and the second exchange is when you transact the data. So if you're doing a read, I'm going to send the address, and then in the second exchange, I'm going to get the data back, right? Or if I'm doing a write, in the first exchange, I'm going to send the address. The second exchange, I'm going to send the data, right? Now you might want to say, wait a minute, hold on. If you're sending the address in the first exchange, what are you getting back from the slave? I mean, what's it got to send? Because it doesn't have an address yet. Nothing. It just sends garbage. You waste it. The SPI bidirectionality is kind of wasted, right, in a way. Because in the first transaction, when I send the address over, and I don't get anything back. The slave just sends random, whatever, zeros, whatever it wants to send. And then in the second exchange is when the data goes, but even then, only one of them is going to be sending data, depending on if it's a read or write. So even though SPI is bidirectional, you don't usually use the bidirectionality of it. Like it's got that feature, but you never use it. It's kind of useless, right? Okay, so So there's two terms here. There's an exchange, which is every 8 bits is an exchange. So every 8 cycles of communication on an SPI is an exchange. But a transaction is when you do multiple exchanges to do a load or store operation, right? So, okay, so here's an example. This actually came right out of a data sheet for an accelerometer or something. You can see that the slave select or chip select, in this case, sometimes the terminology is different, is actually low now. Remember, it's active low. So there's 16 cycles now that this thing is low, which performs 2 transactions. The first transaction is the address, and the second transaction is the data. The address, however, is not just the address. There's also 2 control values in there too. There's a read-write select bit, and there's a multiple or single select bit, followed by a 6. The rest of the 6 bits are the address. Okay, and then the second exchange is the data, right? In this case, it's a read, so I send the address, and then I get back the data, right? So that's a kind of a, let me show you a better, yeah, those 2 exchanges, 1 transaction, right? Okay, right. Okay, so here's an example of that. This is using my waveforms. So, so in the following SPI transaction, assume the transaction address is stored in the least significant 5 bits, and the read-write flag is stored in the most significant bit of the first byte transmitted from master to slave. What is the transaction? So this starts to get a little hard to read now because it's like, okay, there's 16 clock cycles there. How do I read this? Well, I mean, that's 2 cycles, right? I think, 1, 1. And that's 2 cycles, 0, 0, and that's 1 cycle 1, right? But I find that it's easier to kind of mark it up, right? So I'll put these little lines here to separate the cycles, and then I'll translate MOSI and MISO with bit patterns. So now I have exchange 1 and exchange 2. Now in exchange 1, the MISO is all zeros because, like I said, that's kind of wasted. I only care about sending the address out. And then in the second exchange, MISO is also zeros, which tells me this is probably a write operation, right? Because there was nothing to send back. When you do a write, you send the address and the data, nothing comes back. There's no acknowledgement, unfortunately. There's no way to acknowledge that it worked or whatever. You just send it out and just hope it gets there. So I send an address and I send data, and then I'm done. That select goes back high. Okay? Make sense? Now, if I really want to look at this and make sure that it's a write, I have to look at the bits. So remember I said that the least significant 5 bits is the address, and the read-write flag is stored the most significant bit. Notice read has a bar over it, which means if this flag is 0, it's a read, and if it's a 1, if it's a write. So what is it? It's a 1, right? There's a 1 there. So that's a write. I think I have that marked here. Yeah, there we go. So that's a 1. There's the read-write flag. Then the address is in the lower 5 bits, which is just 8. I'm just sending address 8. Now notice there's 2 bits between the flag and the address that are just don't cares. And then likewise, all the MISO bits coming back during that first exchange are also don't cares. And then in the second cycle is when I send the data that I want to write to address 8, which just happens to be 1011, right, which is 11B, and 5, B5. So basically what I'm saying here is I want to write B5 to address 8. And that's the waveform you'd get for that. Okay? So there's, yeah, master writes value B5 to address 8. Okay, now here's an example of a, is this the same example? No, this is a different one. In the following, assume that, all right, so this is the same idea. So the most significant bit now, though, in the first exchange is 0, so this is a read. So now I'm reading, so I'm going to tell it to read, and I'm going to give it an address of, let's see, 1, 2, 3, 4, 5. So 5 bits, looks like the address is 1, 7. No, sorry. No, the address is actually 8 plus 3 is 11, B. Address is B. These 2 bits are don't cares. that bit says I'm reading. So the address is B, and I want to read from address B. So then the slave is going to respond with the data at address B, which is a full 8 bits, comes back on MISO, and that's going to be 1110, which is E0011, which is 3, E3. Make sense? And luckily, yeah, most significant bit first. So I'm reading it in the right order. I was afraid I might have missed that. If it said LSB first, then I had to reverse the order of those bits. Okay. All right, so I'm just about out of time. So there's one other topic here for SPI, and that's what happens if you want to multiple read. You want to read multiple words. In this case, a word is only 8 bits. So if I want to do, like, I will say I want to read like three bytes starting at a certain address, or I want to write 3 bytes starting at a certain address, you can support that too with SPI using more than 2 exchanges in a transaction. But that's pretty simple. So in the first lab that I'll assign this week in lab, we just want you to write a C program or Python, your choice, that will read a text file with these transactions, like a trace of these waveform, text representation of this waveform, and that will decode the transaction, what it's doing, right? So there's actually, this is something that like oscilloscopes, sometimes like later, like more recent oscilloscopes will do this, like where you'll read the data and it'll decode the transactions for you. It'll tell you what the exchanges are, what's happening there, right? But you obviously can write software to do that, which is what the first lab will be. So the first lab will just be a programming project. Starting from lab 2, we'll start doing hardware, right, with the FPGA boards. And I'll introduce that in lab today. Okay, any questions? Okay, great. Oh, there's a quiz too assigned, so make sure you take that before next lecture as well. Just asking questions about this lecture. Well, the deadline is actually class. It's Monday at 2:20. Yeah, anytime before class. Okay, because I'll go over the quiz in class, obviously. So. Sure. Yeah, I could do that. Yeah, I can post the slides for each quiz. Okay, thank you.